Today I will share my recent research on gauge transformations in neural fields. So this talk is correlated with my recent publication of general neural gauge fields in iClear 2023. So here's the overview of this talk. We will start with a brief introduction of neural fields and gauge transformations, followed by the framework of neural gauge fields. So as learning gauge transformation suffers from learning collapse, we further introduced a general regularization method. Then we will introduce some potential applications of neural gauge fields. And finally, we will introduce some existing issues and some future extension of this work. So now we introduce what is neural field. We start with the concept of physical field. For example, a gravitation field. For a point in this space, the gravitation of this position can be computed according to the coordinate by gravity formula. The coordinate of this position can be mapped to the corresponding gravitation via a closed form formula. So this is a physical field. But for a neural field, this formula to achieve the coordinate mapping is intractable. So that means we need to use neural network to approximate this mapping function. Then neural field can be applied to parameterize any physical properties in a space, including 1D space like audio, 2D space like images, and the 3D scenes. And the neural field has been applied in many areas like image compression, neural rendering, and 3D reconstruction. And NeRF is actually a special case of neural field by parameterizing the color and the density of a scene. And this work, we mainly focus on the neural rendering and the neural radiance fields for novel view synthesis. Then we introduce what is gauge transformation. So a gauge, it means a measuring system, like Celsius or Fahrenheit degrees for measuring the temperature. And the Fahrenheit degree can be converted to Celsius degree. And this conversion can be translated as gauge transformation. That means the conversion between different gauges. Besides, we can also, for Cartesian coordinate, we can apply a distortion to this coordinate. And this kind of coordinate, this kind of distortion can be also called gauge transformation. So for 3D scenes, the original gauge is the 3D Cartesian coordinate. And the gauge transformation in neural field means we transform the 3D coordinate to another measuring system. So with the introduction of neural fields and gauge transformations, we now define our neural gauge fields as the combination of neural fields and gauge transformation. So it means we map the original 3D point into another space to index a neural field. The another space can be of any type. Here I list some of them, including 2D planes, tree planes, spherical surface, or codebook, and Fourier space. So here we show some popular gauge transformations that has been explored in NeRF. For example, EG3D is a very famous work on generative NeRF. It maps the original 3D coordinate to a tree plane for efficient scene representation. And similarly, TensorF can also map 3D coordinate to a 1D vector in a 2D plane. There's another very famous work of instant NGP. It maps 3D grid point to hash table index through a spatial hash function. And it achieves scene representation in several seconds. So here is the summary of and the comparison of gauge transformations used in EG3D, TensorF, and instant GP. We observe that the orthogonal projection is employed in EG3D and TensorF, and the spatial hash function is adopted in instant GP. The common point is that all of them use a predefined function to achieve the gauge transformation. So according to this observation, we may wonder a question. So how about replacing this predefined function with a learned transformation? So actually a learned transformation is more favored because it's more flexible and it can be optimized for a specific scene and also for the final training objective. So here are some illustrations to show why a good transformation should be scene-specific. Here we aim to project a curve into an axis. For simple orthogonal projection, so obviously there's lots of overlap during the projection. And for different curves, the axis should be deformed according to the curve shape to achieve a good mapping. That means a good transformation should be scene-specific or object-specific. So here's another sample of projection case in 3D scenes. Here we project a 3D point to a 2D plane. So still, a simple orthogonal projection will lead to clear overlap in the projection space. So it means many different points will be projected to the same position. So this is not desired. And we aim to learn a flexible mapping that can avoid the overlap in projection, as shown in the last figure. Then is how to learn the gauge transformations. Here we define two types of gauge transformation, including continuous transformation and a discrete transformation. And continuous transformation means the 3D coordinate is transformed into a continuous space. So typically like a 2D plane or triplane. And discrete transformation means the 3D coordinate is transformed into a discrete space, which can be a hash table or a code book. Then we introduce learning framework for continuous and discrete case, respectively. So for continuous case, there is a gauging network to predict the coordinate parameters in the target space. The gauging network can directly predict the target coordinate or predict parameters of a certain transformation. Then we can apply this transformation to the original coordinates. So for example, we can adopt a residual transformation where the network only estimates the residual offset. So this method is actually widely used in dynamic NeRF. And we can also adopt a rigid transformation where the network predicts the rigid transformation parameters. Then we apply the rigid transformation to the coordinate. And there are many other transformations that can be explored in the framework. Then we turn to discrete transformation. For discrete case, we aim to map the 3D coordinate to a discrete codebook. We assume the size of the codebook is n. But different from continuous case, here we cannot directly predict the index value because it's an integer. So we adopt a method similar to VQ-VAE for discrete representation learning. For each 3D grid point, we predict a distribution of n dimension. Then the codebook index can be obtained by applying argmax or top K operation to the predicted distribution. So, but the argmax and top K are not differentiable, so a reparameterization trick should be used to approximate the gradient, just by replacing the argmax with softmax in backward propagation. And here is the pseudocode of the forward and the backward propagation in learning discrete gauge transformation. So now we have introduced the learning framework for continuous and discrete gauge transformation. However, we find learning gauge transformation usually suffers from a learning collapse problem. So here for a continuous case from 3D scene to 2D plane, this learning collapse means the learned mapping will collapse to a local region or a small region in the target space, as shown in this figure. So the box in orange denotes the mapped region. All other regions are not used in the mapping. And some previous work introduced a cycle loss to mitigate this issue by learning a mapping to invert the learned transformation. So with this cycle loss, we can observe the collapse is indeed mitigated in certain extent. But the 3D points are still mapped to a local region. And most other regions are still not used in the mapping. So this result is still not desired. So similar things happens for discrete case. For discrete case, we map 3D coordinate to a code book. And for the figure, the x-axis means the code book index. The y-axis is the number of mapped points. We observe that these 3D points are only mapped to a small number of indexes, while most indexes or entries of the code book are not used at all. So this learning collapse or codebook collapse is a common problem in VQVAE, which is still not well resolved. For this discrete case, we can also apply the cycle laws to regularize this transformation, but we find it doesn't work at all, as shown in the figure. Most codebook index are still not used. So now we need to think of a good method to regularize the transformation to avoid the learning collapse problem. Here we still consider the cycle loss. So we know it's a loss in cycle gain to preserve the key information in image translation. So for neural field, we aim to preserve the scene information during gauge transformation. This preservation of scene information can be achieved by maximizing the Marshall scene information during translation. So we term this regularization or this loss as information regularization. Yeah, here we assume X are the original point, Y are the transformed points. PYX and QY are the posterior distribution and the prior distribution. Then we can compute the Marshall information according to the formula. So by maximizing this Marshall information term, it can be easily transformed into another formula, which consists of two terms. So then we need to solve these two terms one by one. So for the first term, we need to replace the unbounded KL divergence with upper bound JS divergence. Then according to the Jensen-Shannon Marshall information estimator, this term can be estimated by below form. So this form is, he employs some negative pairs and positive pairs to estimate the JS divergence. So this form is similar to the contrastive learning or the InfoNC formula. So actually, this cycle loss can be regarded as a very special case of it. So now we have solved the first term. We turn to the second part. The second part is actually compute the discrepancy between a prior distribution and a posterior distribution. So the prior distribution is different for continuous case and discrete case. So we should handle them separately. For continuous case, we expect the prior distribution to be a uniform distribution in the target space. So as shown in the first figure, is an example of 2D plane. We sample some grid point in the 2D plane. So that all the region or the feature in the plane can be used uniformly. The posterior distribution can be approximated by sampling the mapped point according to the radiance contribution. So now we have samples of the posterior distribution and the prior distribution. Then is how to compute the discrepancy according to these samples. And here's the illustration. The original KR divergence is not suitable to measure the discrepancy because the geometry of the 2D plane is not concerned in KR divergence. So here we need to replace the KR divergence with the Earth mover's distance. The Earth mover's distance aims to measure the minimum distance required to move a set of points to another set of points. So with this function, with this Earth mover's distance, the mapped point or the posterior samples will be forced to fit the prior distribution. So as a result, the mapped point will occupy the full target space, like as shown in this figure. So that means it will not collapse to a local region. Then for discrete case, the computation is more simple. Here we expect the prior distribution to be a discrete uniform distribution. Also, all the features in the codebook can be used uniformly. Or we can say that the information can be maximized. And similarly, the posterior distribution can be approximated by summing up all the predicted distribution of all the points. So then the discrepancy can be computed by a simple KL divergence or another simple L1 loss. So now the derivation of information regularization has been completed, and we validate this regularization on both continuous and discrete transformation. So as shown in this figure, for the mapping from 3D space to a 2D plane, without our regularization, the map point will, with our regularization, the mapped point will occupy most regions in the target 2D plane, and instead of falling into a local region, which is much better than the original learning continuous or the cycle consistency loss. And for the mapping from 3D space to discrete codebook, we also observe that all the codebook entries are used for the feature encoding, as shown in the last figure. So this method can help to avoid the codebook collapse. So we can also explore this regularization in discrete representation learning, because yes, codebook collapse is a common problem. And now the main method part has been done. Then we show some applications of neural gauge fields. So as it can learn a transformation between two spaces, so we can use it to learn a mapping from 3D space to a UV space. That means we can get explicit object texture from 2D images. Here are some results of the learned UV mapping. So including the synthetic nerve and the DTU data sets. But we can observe the quality of the rendered image is not that good, because we index the radiant field in a low dimension space. Here is the 2D UV space. The original nerve indexed radiant field in the 3D space, so the rendering quality is not high. The advantage is that we can get the explicit explicit object texture. So that means with this explicit object texture, we can some texture editing task can be performed. So as shown in this figure, here we mapped 3D scene into a sphere surface. We visualize this sphere surface by the cubo map. So we can directly replace the texture with other patterns or textures. And we can also ensure multi-view consistency of the rendered images. So here I just show some very simple applications or very straightforward application. So as a general framework, there are more potential applications can be explored. For example, we can explore to learn using the neural gauge fields to learn a flexible mapping to project dynamic scenes to tree plan. So which can lead to better rendering performance. So also for intrinsic decomposition, the current method mainly relies on NeRF for the scene representation, and then the object surface can be extracted to perform the intrinsic decomposition. That means the intrinsic decomposition is performed on the object surface space, but with neural gauge fields, the intrinsic decomposition can be performed in a 2D space, like a 2D UV space. So it allows some local intrinsic editing, and also it allows the end-to-end optimization for intrinsic decomposition. In the object surface space, it's very hard to perform some local editing because it's actually in a 3D space, or a 2D manifold in a 3D space. So besides, SK transformation can learn some more flexible mapping. So it can be applied to achieve compressed scene representation model. So this, this application has been explored in this work. They just replace the predefined spatial hash function in instant GP with a learned discrete transformation. And the model size can be compressed a lot, but preserve the rendering quality. Because in instant GP, he used a predefined spatial hash function, which is actually not flexible and cannot be learned. Then I'll introduce an existing issue that I'm working on for the extension of this work. So, it's, I have to say it's a very interesting problem. Here we show the original projection and also our regularized projection and the mapping path. So still, the orthogonal projection can only occupy part of the space, and it can also lead to many overlap during the projection. And our regularized projection can occupy the full space, and of course produce less overlap. But but the problem is that in many cases, the orthogonal projection can lead to better rendering performance. So this is actually counterintuitive because the regularized projection can use more space in time, can use more region and space, namely more features to model the radiant field. But the performance is even worse. So it is very strange, and I would call it a paradox issue. So now also not validated, but I guess it's caused by disordered mapping. So as shown in this in the mapping path, there's a lot of intersections between different paths. So that means this this learned projection is highly distorted or disordered. Also, the regularized projection can use more features in the plane, but the mapped points are highly distorted and disordered. So it can lead to some gradient problem in the model training. So I need to verify this issue, and that's what I'm working on now. And so here I provide a possible method to handle this problem. So previously we just estimate the coordinate for each point. So we need to, so this point is under constraint. It can be mapped to any position, and it can cause the distortion, disordered. So now we just predict some key point. So that means we just predict some spatial transformation network. We directly predict this key point, and this key point can be applied to transform the original 3D point. And this transformation can keep the structure of this point and will not lead to distortion or disorder. So that's initial exploration, and so it's not verified now. And there are also some other solutions. For example, we can try some loss function in non-rigid NeRF to preserve the local structure. But the main concern is that this loss function can lead to very high computation cost. so I do not try them. So as a conclusion, yeah, I would say our work is using the neural field to optimize the gauge transformation. So this is the main part of this work. And so now we can spit out this work. So neural field is a model parody. It can be applied to various tasks in addition to rendering. So also most work use neural field for rendering and reconstruction, but it can be applied to more tasks and areas. So for example, here I list some applications that has been explored. Neural field for visual analysis. Yeah. The first is our work. He optimized the gauge transformation with neural field. There are also other works like NEMO and VMRF. They optimize the camera pose with neural field or neural rendering. Also, there's a panoptic lifting. It's a 3D aware segmentation method from 2D annotations with neural field. And there's also another work called feature fields. It utilizes the neural field to achieve 3D scene decomposition from 2D images. And there's also NeRF supervision. It learns dense object descriptors with neural field. So I mean here, neural field can be applied to nearly all kind of visual perception tasks. So there are two types, perception or synthesis. So synthesis has been explored in many works, but the perception is still an open challenge, and it's also an open mind problem. We can also explore neural field for 3D detection. I believe that was exploration. So besides, for superiority this year, we are also organized a workshop on generative models for computer vision. And this workshop mainly explore how visual analysis can benefit from visual synthesis, including neural rendering. So neural field for visual analysis will also be covered in this workshop. So if you are interested in this topic, you are welcome to join the workshop. And yeah, that's all of my talk, and thanks for the listening.